Okay, hello everyone. Yeah.
So up to what chapter 2 are we having a quiz on?
Quiz?
Yeah.
Okay, good question.
I just got here and we're already having a quiz.
Yeah.
When?
This Thursday.
Okay.
So it should be about functions. Okay. So that will be chapter 1. And about limit until condensation. Yeah, until the limit. I think I will talk a little bit about this one, continuity, and also the limits at infinity. I think those two will also include. Okay, so please pay attention on today's class. Okay. So yeah. So why we are having quiz a little bit early? Because I would like to know, like, how much you are on average level. Like, I would like to know, like, the results, so that I can adjust the content. And also, as I mentioned, we skip for a while the precise definition, and I will give you just the additional material about that. And we're focused now on the next one, which we are going to discuss on continuity. Okay? No. Okay, so continuity. So let's see. What's the? Let's see just this graph. Okay. So before we define what is continuity in terms of mathematics, so let's just see the graph. Okay, we see this one here, curve, and then the curve going there, right? And you will see that if we have, or if you see in any graph that has this kind of circle, it means that there is no point on that curve, okay? Or we can say like a hole. So, no point. Okay. Previously, before, we learned if we take limit, for example, approaching 1, as x approaching 1, go from left, go from right, we can get the limit, right? Okay. But if we draw and then just say, is the function, this one, is this curve continuous? No, or yes? If we look on the whole thing, it's not continuous, right? But somehow, if we take maybe just this part, we can say it's continuous, but only this left, right? And then we can say it's continuous on the right side, only, right? But if we see the whole curve, we say it's not continuous. Okay, now, if we look this part here, we can say this is also not continuous, right? It's obvious because they are far apart, right? So, I think it's easy if you are drawing a curve, whenever your hands, like you draw, whenever your hands pick up like that, and then you draw again the curve, you can say that can be discontinuous. So it's not a continuous function. So when you draw, like, for example, draw like maybe on the left here, and you see, okay, we have something missing, right? Okay, now visually we can see, right? But we need also to write in terms of mathematics. How can we know that the function is continuous or not? Okay, we already defined the limit, right? So we can find this limit, okay, limit from the left, from the right, okay, we have limit here. But how do we know that we have continuous function? To be continuous, this whole, for example, should be a point, right? Should be, we need to construct some point here to make it a function. It means that the limit need to be equal with the function at that point. You get it? So let me write here. I think you can just focus here. I think it's already simple enough. Okay. So if we already find the limit, okay, we can get the value is equal L, for example. And then if we plug in A into the function, we get the same value L. It means that the function is continuous. Okay? But of course, this definition need to be at least you need to have some requirements. Okay. So first requirements is this f of a need to be defined. Okay. Which means you need to also consider domain and so on, right? Okay. And number two, the limit as x approaching a of function of x. We need to also prove that this limit exists. Which means we need to left and right has some value, and then we say, oh, it exists. Okay. So then at the end, we can say that this limit equal the function at point A. They are equal. So we can say that, okay, the function is continuous. Okay, some naming, well, but I don't think this is necessary, but we call this removable discontinuity. This one here is jump discontinuity. And if you have maybe asymptote, you can also have asymptote discontinuity. Okay. Like this one, maybe going down like that, and the other one is here. We have this one here. We call this is asymptote or you can say infinite discontinuity. It's also okay. Okay. Oh, I think I have the picture here. Let me just go here. Okay. Okay, I think it's okay. Okay, we can also write the continuity according to the one we approach. If we approach only from the left, then we say it's continuous on the left side. Or we approach from the right, we can say it's on the right side only. So we can also make one side like one side limit. And at the end, by definition, the function is continuous, okay, on the interval if it is continuous at every number of the interval. So you need to be aware of when a function has probably some restriction on domain, perhaps maybe some discontinuity might happen. Okay? So you can check first the domain, which interval it can be continuous. Okay? Okay. Okay, let me go through. Okay, some theorem. It is up to you if you want to write this or not. Just additional information, but I think it's quite intuitive. So I don't think you need to write this. Okay, but if you want to write, it's up to you. Okay. So of course, if we are having continuous functions like f and g, we can treat them like we can add them, we can subtract them, we can make multiplications, or we can divide them, or we can multiply with another constant. Okay. And of course, polynomial functions, they are continuous everywhere, continuous on every real number. And the rational function, of course, it will be continuous if we know where the interval is. If they have some certain domain, then we need to be aware of that. Okay. And one simple note on the trigonometry, I think this is quite easy to understand. If you have cosine, if you have sine, you know the graph of sine and cosine. If we draw a circle, we can see that this is a circle with radius 1, and we can convert to the circle, right? The sine and cosine, and we are going to see that when the theta approaching 0, cosine is 1 and sine will be 0. I think that will be very intuitive, and I believe you also know the trigonometry, right? Okay, I think we can skip that one. And this is also additionals. Some function that it is probably like most of the function that we have in calculus 1, they are in our assumption by default they are continuous. Okay, you can say that. And then we can also perform this composite function. We can plug in the function g inside f and take the limit. And by doing so, we can evaluate only the limit of g, okay, with inside the function f. Okay, we can do that as well. Okay. Okay. What else do we have? Oh yeah, one more about the composite is if the g continues, f continues, and of course we say it continues at a, continues at g of a, then the composite they are equal f of g of x is continuous at a also. Okay. Okay. now one important theorem that I think this will lead to our calculus 1 thing, at least the first theorem to sketch the graph is the intermediate value theorem. So intermediate value theorem is if we have a function that is continuous, let's say f, and we have an interval ab, a closed interval from a to b, and then we can set some n in between the y-axis, between fa and fb, and we can set n. And then there will be a number c in between the interval ab, such that when we plug c, we are going to get n. So it means that, let me write here, oh yeah, I have the graph. Maybe here, it is first. So, suppose that this is n, okay? And this is the interval a and b. The theorem says that in between this a, b, there will be a number c that when we plug in, we are going to get this. Okay? So this will be c. Let me write here. Okay, that will be c. And this is what we call the intermediate value theorem. Okay. So for example, let's say we have right here. And of course, if the curve, like, for example, it has many c's, it can be, because it can be done also. It's not always only one c. So if we have a function, let's say it's a normal polynomial with some degree. So if we can set some interval, and then we can try to plug in some value, if we can make sure that, okay, there will be something in between. For example, let me show you. 4x cubed minus 6x squared plus 3x. Okay, show that, let's say we have this f of x, let's say we have f of x, let's say. Show that there is a solution. Let's say between 1 and 2. Well, it's already directly given, so you can just try. For example, we take f of 1. Okay, so we take that 4 minus 6 plus 3 minus 2. What's that? -1, right? And then this is, I think, pretty simple examples. So we could just take 8, 4, 32. Okay. It's 14 minus 2 is 12, right? Okay, the first one is negative. The second one is positive. What's the implications? What's your conclusion? We are not necessarily to know how the graph will be, but we know that when we plug in one is negative. It means below the x-axis. We plug in 2, it's above, which means they need to cross x-axis, right? So there will be something in between. So it's proof that by intermediate value theorem, there exists some numbers in between. Okay, get it? Okay, so let me just draw here, okay, just to make sure that we are clear on this. So let's say this is 1, this is 2, or maybe 2. So this is 1, this is 2. When you plug in 1, we get around here, right? This is F1. Okay. When you plug in 2, maybe around here. So no matter how the graphs will be, you know that the graph should be connecting this to here, right? Maybe like that, or maybe like that. We don't care about that. But for sure, we have shown that in between 1 and 2, there will be a solution which is when it's equal to 0. Okay? So we can say, or we can write that F1 is less than 0, less than F2. That is, we can say n equals 0 is a number between F1 and F2. So at the end of the day, the solution or the equation 4x cubed minus 6x squared plus 3x minus 2 equals 0, at least have one solution C in between 1 and 2. Okay, this, I think, one simple way to apply the intermediate value theorem. Okay. Okay. Okay, I think we can go to the next section. And then if we have time, we can review all. Okay, the next part is we call the limits at infinity. So for a moment, let's take this graph. Okay, we have this graph, x squared minus 1 and x squared plus 1. You see that we have also line y equal 1. Now if you plug in x, either going to the left or going to the right, you will see the number, okay, when you plug in, it's going to be equaling to closer to 1. Okay. So you could try for some x. Let's say if we try 0, x0, f of x is just -1, right? Just with the functions. And then if we try, let's say 1, it will be 0, right? Both plus and minus 1, right? And then if we increase again plus minus, because both sides they are symmetrical, we could see that maybe this will be like 4, 3 over 5, which is 0.6. And you will see that when we increase the number, let's say 100, it will be around 0.999 something. If you increase and increase, it will be getting closer to 1. So by our intuitions and by what we have learned so far, this is an indication that we can use limit. Okay? So we can express this in limit symbols. So as we increase x as large as possible, or we can just write getting to infinity, then this seems to be equal to 1. Okay, or we can just simply use the notations, just f of x, and then this will be equal some value L. Okay. Or you can see the intuitive definition at that one. Okay. So if we have a function defined on some interval, then we can say that we can make it large and large and large. And then when we make it larger, the number is getting too close to some L. Or we could just simply say L. The same way, usually we have this interval, a positive interval, let's say. And if we have another one that is on the interval on the left, I mean the x is getting, you can say getting smaller, but I would like to say getting larger to make it easy to understand, getting larger, but in a negative way. It means going to the left, right? It means that x is getting approached to negative infinity. And the same way, we can express it close to L or just simply L, okay? In some of the graphs that we might encounter in the problems are, okay, you see that if we make it large on the positive side here, it's getting closer to this y equal L. Okay, it means that it's getting close to L, right? Same way with this. Somehow it's getting closer. So it's never going to be crossing this line. Okay? So it's going to be closer, closer, and forever will be stays like that. And also you can have some kind of like oscillation. So you can have like up and down, but the amplitude will be smaller. Okay? So it will be getting reduced, and then it will be getting closer to this also L. Okay? We can also have that possibility. It's not always like the graphs, like never crossing, but sometimes like it's crossing, but it's going up and down, up and down. Okay, we can also say that it's getting closer to L. Okay, this is, I think, get the conclusions, okay, that we can have the horizontal asymptote. Okay. Now you could guess if we have this. If we draw the curve, okay, let's say that's our graphs, and we could see that by this graph that we have this asymptote, which is y equals 0. Right? So as x getting larger, either to positive or negative side, 1 over x get closer to 0. Okay, so either we take it like that, or if we take to the left, it's also 0. Okay, now I would like to give you some practical applications on how to use this. Okay, maybe before that, just notes on the tangent inverse. I think we can skip this one. Tangent inverse, in tangent we have the asymptote, right? In tangent we have the asymptote on pi over 2, negative pi over 2, and if you want to make it a function, then we need to limit the interval. Okay, we need to restrain the domain. Okay. So the theorem, okay, for 1 over x with power of r, and r is, we can use it's a rational number that is positive, then we can write in general 1 over x to the power of r with limit x getting close to infinity or getting larger is equal to 0. Okay. In the same way, when we take to the left, it's also equal to 0. So if we take limit, for example, can you compute this? So by taking the principle that 1 over x in limit is 0. So, and 1 over x with power of r, which r is the positive number or rational positive number. So 1 over x squared, 0, right? 1 over x cubed, also 0. Okay? So the point is, if we have this kind of rational expression, taking limit, and you see that the x is getting larger, okay? So what do you do? Any idea? Any idea? What do you do to solve it? Any idea?
And 0 over 0 and then third superpose. That's right.
Factorize. Maybe. Yeah, any other maybe? Did you have any? Ah, yeah. That's the fast, the shortcut. Yeah, the shortcut. I'll feel it. Yeah, but that's true. Look at the polynomial degree. Degree 2, the highest one. Okay? Degree 2, the highest one. Okay? So by the definition that 1 over x with power of r, when we put limit, it will equal to 0. So that means this, all of this will make it to 0, and the left one, the 3 over 5. That's the answer, 3 over 5. But let me give you step by step how we do that. Okay? So, yeah, you could say that if you know the degree, you could solve this less than 5 seconds. Okay. So, let me give you how the process will be. So I would like to start with we divide with the highest polynomial degree, which is x squared, okay? So 3x squared minus x minus 2 divided by x squared, and then the same thing we try to do here, divide by x squared. And then this is 3 minus 1 over x minus 2 over x squared. And 5 plus 4 over x plus 1 over x squared. Okay? And then we can separate the limit, right? We can separate the limit. I think if you are joining some cram school in your when you're still high school, you will get a shortcut. Or maybe let me write here. Okay, get it? So this will be 0, 0, 0, 0, and we are left with a constant 3 over 5. Okay. And the same way, when you see the polynomial degree, maybe one is higher than the other one, you could get directly the answer. Either 0 or it will undefined. Okay. Or if it's the same, then you could get a constant. Okay. Okay. But the shortcut one, okay, the same degree, you see the constant is 3 and 5, okay, you could ignore the other one, okay, it's 3 over 5. Especially if you are having a multiple choices in the question. But we will not have any multiple choice in our exam. Okay. Too easy, right? But it doesn't matter like easy or not, as long as you have good logical thinking, reasoning, and how to express your solution. I believe that it's okay. Okay, it's okay. Okay, another example.
So the rules basically, it's not just 1 over x r, it's always any constant over x.
Yes. Basically, yeah. Depends on the equation. If there is just additional information that you don't need to prove for the answer, I think you can do it. But of course, the question is not as easy as that, right?
Assuming that there is no shortcut, what do you do? You go and just rationalize. No, you just divide by the higher power. And then actually down to shortcut. Yeah, that's what you do. That's not a shortcut. That's not the shortcut.
Actually, there is no shortcut in life.
That's not a shortcut. It's just like
It's just how you solve in your mind. Okay, how you solve in your mind. But somehow, we learn through some maybe some cram school, and what you remember is, okay, I can do this faster. But it's actually, if you think carefully, what we did is correct, right? We just defined with the highest degree, and we found that something over x or x squared, the constant, it will be required to have 0, right? That's the idea. Okay, how about this one? Okay. So whenever you have any square root, and then you have another component plus or minus, what you can do, you can try to rationalize. We call them rationalize this root. Okay. So we are multiply this, and then based on what we have in the algebra, if we take this multiplication, we are going to get this, right? So we are going to force out this expression because we want to remove the roots. Right? At least we're getting a new expression from this multiplication. So we take so let me write the question again, and then multiply with. But of course, if we want to multiply, then we need to make it like this, right? If we just multiply with this, what reasoning we have? Why we need to multiply, right? But if we just multiply this is okay, right? Because this is just 1, right? But what we do here is we need to modify the expression. We need to simplify it in some way. So it means we are going to have, on the top, we have the x squared plus 1, or let me write here, x squared plus 1, and then minus x squared. And in the bottom one, we have the square root, x squared plus 1 plus x. And then we have limit. This is 1 over okay. Now we are sure that this the denominator is positive function. So any x you put in, this should be positive, right? So as this is getting larger, 1 over something that is really large in limit, then it becomes 0.
Become large as x. Okay, before break, let me write one more. This limit. Okay. Okay, I think we can continue. And if you see this limit question, I think it's sufficient to say that if you intuitively look at how we can approach this x to this number 2 from the right side, then I think if you considerably think on the tangent inverse or maybe just tangent, like you know the tangent, it has an asymptote on pi over 2, negative pi over 2, right? So when we think this 1 over x minus 2, it seems that this is going to be an infinite, right? But I think the best way to confirm, we can make sure, okay? So we can make sure by taking another variable that we can make. So let's say we take t, okay, and let this t equal to 1 over x minus 2, okay? And from this expression, if we take x approaching 2 from the right, okay, you could imagine 1 over x minus 2, okay? Remember 1 over x like that, right? So you could imagine 1 over x minus 2 and then you move to the 2 units to the right using some transformation function. That will be in your quiz. And then we take this to here and approach this, and we see that the t is getting larger, right? So as x getting closer to 2 on the from the right side, then we get t is getting close to infinity or getting larger. Okay, so we can exchange this by this new definition. We can rewrite limit. Let me write again here. This equal, and then we can exchange the x with t, and then we can just imply that this will be the t, which of course this is based on what we have in the tangent graphs. This will be equal to pi over 2, okay, because only on the right side, on the first quadrant of the trigonometry, okay, so it's a positive pi over 2. So sometimes you could do this.
Where did I come from? Pi over 2?
And then come from the tangent. Okay, that's okay. So tangent pi over 2 is infinite, right? Remember the tangent graphs? It has like that, right? And it has the asymptote like that. Okay.
Okay, another thing that is, I think we need to discuss for a while is, let me erase this and let me write limit as x going to the left, okay? And then we have e to the x. This will get into 0. Okay, so if you remember the e to the x, the graphs, it will cross 1, right? It will cross 1 over here, and then we have that. Okay. So if we look at these graphs, we get the idea that when the x getting to the left, to the negative infinity, then the functions will approach 0. Okay, so we could see that this has the asymptote on the y equals 0. Okay, and then I think that's it for this limits. Okay, the infinite limits at infinity. Okay, now we move to the limit, okay, which relates to later definition of derivatives. Okay, I think at the early classes we have discussed about this. Okay, so we approach, let's say we approach this point P from the Q, and we say we can have a tangent. Okay, a tangent, or first maybe the secant, the blue one is the secant, and then as the Q moving to the left, approaching this P, you see the line previously between PQ is getting closer, and then this blue line is getting closer to the red line. Okay, we call this as the secant line, the line that is cutting the curve, and then it's going to reach this red line, which is the tangent line, or the line that is touched only one point at point P in this one. And then we define that, okay, we can approach that. Actually, by definition, the slope or the gradient, or you could say the tangent, is actually limit as x approaching a, f of x minus f of a, which is, this is coming from this triangle that you have learned before, I think, when you learn the slope line equation, right? So this over this is your gradient, okay? And using limit as a concept to approach this Q to P, or x to a, as we mentioned in these equations, then we can define this as our slope, okay, as our m. Okay. But we need to make sure that limit exists. Okay, so assumptions, this is provided that limit exists. Okay. So if we try to, let's say we have the y equal x squared, and we have point P, let's say point P is 1, 1. So in the process, using this limit definition, then the slope is limit as x approaching 1. So we want to know the slope within this curve at point P. So we take the definition, f of x minus f1, and then x minus 1. So let me give you the process first. And then we solve the limit. I think we can factor this. So we know that this will be equal to 2. Okay. And then usually the question will ask like, what is the equation of the tangent line? So the meaning is we have m equal to, and we have the point that which is p, that is 1, 1. So we can apply this line equation y minus y1, m, this is x. These are usual line equations that probably you have learned before, right? So y minus 1 and 2, x minus 1. So this will be y 2x minus 1. Okay, so this is a type of equations or questions that perhaps a typical question that might be asked for most calculus chapter, especially the derivatives part. Okay? So we'll ask the tangent, the slope, and then the tangent line. Okay. So I think the idea is very simple, but how we compute it depends on how much we're familiar with the algebra. Okay. Because of course the function is easily enough. Okay. Even without derivative, we can use the limit. Okay. Without the derivative techniques. And later on you will learn how to solve using the derivative techniques. Oh. Careful, careful. Okay, another way to write this limit form is by taking it's very similar, but we are taking a to a plus h. We are going to look at this additional h as a distance from a to this point a plus h. And we exchange all the terms, becomes a plus h, okay? And then the same thing, so it's very, very similar. The same thing, we can write down that the slope is limit as h now is closer to 0. Okay, so we could also write that. Okay. So either way, use the first one or the second one. They are basically the same thing. Okay. Sometimes when you learn some problems in derivatives, you try maybe many techniques using derivatives, maybe not really satisfied. Maybe sometimes it can be solved using the limit. Some questions. And also, we could rewrite or using the same formulation of limit to define the velocity. So if we have a position, okay, that we have the f as our position function and time is our variable now, then we could describe when time is equal a, then we need to describe the velocity at a. It means that this VA is our instantaneous velocity. Or you could say that this is actually still the slope. Okay, the slope. So if we imagine that the curve is position or distance, then the way we change its velocity, then we actually change the slope. Okay? So if we can make it into graph, then we could also change whether it's going to be fast, slow. Okay. Okay. What else? I think this will be the same for every section here. And this is actually the same thing, but actually the slope that I mentioned earlier, that is actually our, what we call the derivative. Okay? What we call derivative. So we can define the derivative as limit f(h) goes to 0, and then f(a) plus h minus f of a divided by h. Okay? Or we can write using the terms at the early explanation. So f of x minus f of a over x minus a. So basically, what we deal before the slope at one point is actually our description on derivative, right? The first derivative. So if we have a curve, we could describe what will be the first derivative of that curve, which means if we have, for example, this one like that, or maybe let me write completely, maybe like that. So we could describe, if we could pinpoint at every point of the curve, okay, we could imagine there will be a slope or a tangent. Let me write like a really small like that. For example, we have a slope like this. Okay? It's quite steep. And then the slope seems getting flat, right? So we could imagine from maybe quite positive becomes 0. And then from 0, it's become going down. It's more negative. So you could imagine, and then we could also describe, if we want, to make out another functions which describe the derivative of that function. Then that will be our goals, I think, in a few chapters in the future. We are going to sketch a curve using calculus. Okay, some examples. I would like to show some examples, but I think the examples will be worth it if you are already familiar with some simple derivative. So I would like to skip and then going through here. Okay. So as I mentioned, this is just a warm up to sketching the curve. So we have a function like this. The idea is we are going to use this function and then write down the graph of its derivative. Any idea how to do that? I show you that the first derivative actually the slope, right? The slope. So let's take closely. So we know the slope here, right? It's going down. But the problem is we don't really sure how negative the slope is or how positive the slope is. But which slope do we know for sure? No. We're not really sure about that. Because there is no mentioning any necessary points. But what for sure? Like you're given just a random function, and the question is, can you make the sketch of the first derivative of that function? What would you do? The first thing you need to do.
Negative? And is it?
When it's changing from
Yes, and what is that? Yeah, the slope is equal to? Yeah, that's the definition of slope, but going to 0. Okay. For sure we know the slope that is horizontal, right? Which is equal to 0. Okay? So I think we can start by taking that. Okay. So let's say this is when m is 0, m is 0. And then let's make up the graph from there. And then let's say we're going to have this long and then we translate all the points. Let's say we have this point, let's say this point here, translate to here, okay, and this other point here. Okay. Now for sure, that if this is the first derivative, okay, if this is the first derivative, the curve of the first derivative should be crossing this and this, but from where to where? Okay, then we can see. What will be this one? Negative, right? So let's say, let me just write, and this is just assumption, okay? So let this m, maybe, let's say -1, let's say -1, okay? But we know that this is negative, okay? So, we have at least two possibilities for this crossing. It can be like this or this, right? Which one? Yes, because the slope is negative and this is the negative value, right? So we are going to have something like that, okay? So perhaps this is going to be, let's say here, going over there, and then let's say this is the point. So it's going through over there. And then, okay, this is a little bit tricky. From 0, it's getting positive. Positive, or let me just draw to give you some clear explanation. So let's say this is the slope, the slope, the slope. Okay, at certain point of the slope, okay, it's getting positive, but positive, I mean larger, right? Larger, 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 but then it's getting smaller, but still positive, okay? Still positive. It's getting smaller, smaller, smaller until it reaches 0. Can you predict where in the derivative, which one is the maximum one? Here, right? Yes, here, right? Around here. When you see from the larger and then it's getting smaller. That change, later we call it inflection of change, that's the maximum of the derivative. So from this one here, let's say imagine that this is the change. Okay, let's say this is the change.
So it's getting larger, larger, and larger up until this point. Okay.
This is positive, right? This is negative, right? And it's getting smaller, but still positive, right? Still positive. It's getting smaller until that m equals 0. So we are going to cross this. Okay.
Okay. Maybe it's not smooth. Okay.
And then what's happened? Okay, we can see from
The right of the curve that we are going to have, okay, start to getting negative, negative, bigger, bigger, and then at certain point, perhaps it's getting
getting, how to say that, increased but still negative. Do you get my point? You see it's getting like steep and then it's getting a little bit not too negative, but still negative.
So you could imagine that perhaps here, at this point here, is maybe another what we call the inflection point, or now the minimum one. Okay, the minimum one. So perhaps this is, and we don't really need numbers now. This is just warming up how to sketch the graph by assumptions from the slope. Okay. And then perhaps this is maybe like that. Okay.
Because at the right side we are not sure what will happen, so we could just stop. We can do that. Okay. So my point here
Is
from this slope equals 0 and then slope negative and positive, you can imagine how the derivative can be sketched. Okay. From the functions, and then you can sketch the derivative. This will be tricky later in it, I think in chapter 4, when we learn how to apply derivative in the, especially for graphing the sketch and observing the sketch. Okay? And careful. When you read the questions, sometimes the questions give you indications. The graph is f, or the graph is f prime, or first derivative, or even second derivative. There will be some notions about that, and we are going to think a few weeks later. Okay, going to take that. But at least now you can have some idea on how to take the sketch. Okay.
I think just checking your limits understanding. Let me go for some examples, okay? I'm also curious on your quiz, and I don't want you to get a not really good experience. So let me try questions. So example. So exercise limit. For what value of constant C is the function f continuous on all interval if the function okay, let's try this one.
We're continuing the graph and the limit derivative next week. Okay? Or maybe next after the quiz. So quiz 1 hour, class 1 hour.
So let's say we have this question, and I think this is also one of the typical questions. So what value of constant C? So where C is on this one, and we need to guess or to determine what is the value, so that the function is continuous everywhere. So remember, in continuity, I think I've explained it at the beginning of the class. What should we do first? Okay. Yeah. But we need to make sure we see that it's continuous.
Do we need to prove it?
Yeah, to prove it using continuity. Yeah. Because if not, then maybe the graph will not meet. Yeah, we need to. So imagine you have like a two curve. We need to make sure that with this C, the curve is matched and then continuous. Okay. And because this is C, we are not sure how does the curve will be. Because it can be in any C, right? It can be any C. We need to try to use some equations that state that, okay, we can make this equal, right? How to make that equal. Of course, you can see it very clear because it's cubic, it's square, how does it equal? But in terms of continuity, if you remember what we have done at the beginning, the first thing is take the limit, okay? And then check the point, right? And for the first step, that is correct. The first step is correct. I should continue. Do you understand the question? Okay, so the idea, if you want to make it continuous, then if you look at the f, the interval, they are at least continuous on this and this, right? So if we take the limit approaching 2 from the left, then we can write the value, and then we can just plug into 4x, so we have 4c plus 4, okay? And then taking the limit as x approaching 2 from the right, then this will be equal to 8 minus 2c. And then assumptions, okay, assumptions, f is continuous. So then 4c plus 4 equal to 8 minus 2c. So it will be 6c, 8, or this is 4. Or c is equal to 2 over 3. So with this values 2 over 3, the f would be continuous. When c is 2/3. Okay, any questions? Any questions on this? This should be okay, right? Should be okay? So what you need is just to find the limit from the left, from the right. And the assumption is continuous. It means limit from the left equal to limit from the right. And then evaluate the limit and you can find a value of c. This type of question, it can come with many variations, but still the idea, left hand limit, right hand limit equal. And also, if there are some numbers that need to be put inside the function, then you need to also to try it. Okay, do you want another question? Okay, another question. Find the numbers at which f is discontinuous. At which of these numbers, I hope it's clear, is f continuous from the right, from the left, or neither? Not from the left, not from the right. The function is another piecewise function. So based on the interval, I think you could try to take the limit as x approaching some interval, right? You could see 1, 1, 4, 4. You could try these two numbers, 1 and 4, right? Okay. So find the numbers at which f is discontinuous, at which of these numbers is f continuous from the right, from the left, or neither. Or if you are still confused on how to wrap up this piecewise functions, you can start look the interval. Look the interval first. You have x less equal 1. So you have 1 maybe here. And then you have another interval 1 and 4. So 1 and 4. So you have something before 1, which is 2 power of x, that is your graph. And then between 1 and 4, it's just a linear 3 minus x. And then a square root of x, when you have greater than 4. So you have 3 curves. The function has 3 curves. Okay. And I think this kind of function is easy to visualize if you want to maybe make some guess. And sometimes when you're solving some problems in calculus, if you are not sure whether it's correct or not, sometimes drawing the graph may be helping to confirm your solution. So you can try to draw also, okay, to see is this correct or not. Okay, we know that we can have all this as simple functions, right? I mean, we know how it looks, and we know that based on the interval, they are all continuous by default, right? So within this interval, this will be continuous. Within this interval, this is continuous. Okay. So I can write for just for the beginning, we can write the f is continuous. Let's say from the left, like that, and then the middle one, and then the right one. Okay. And now we can start taking the interval one by one, okay, by looking at this and take the limit. Okay. So we can start by taking the limit, for example, as x approaching 1. Okay. Let's start from the left, which means that the function will be 2 with power of x, right? On the left. Okay, we can just compute by direct substitution that this will be 2. Okay. Now, similarly, we are going to do it for the right side. Okay. Which is which function? The second one, correct. Okay, good. So this is 2. Okay. Then we can write conclusion that limit as x approaching 1 of f of x is equal to . And by doing so, we can also compare with the function itself, not the limit. Then when we plug in 1, either to both 1 and 2, 2 with power of 1 is 2, 3 minus 1 is 2. And it's also the same. So the function itself is also equal to 2. Which means, from these two expressions, it means that we have continuity at x equal 1. Okay. Okay. The next part is obviously based on the interval we see is 1 and 4. So let's try number 4. Okay. Try x approaching 4. So let's take x, limit x approaching 4. Let's start from the left. So from the left means the 3 minus x. So we are going to evaluate direct substitutions. This is going to be -1. Okay. And then from the right, this will be square root of x, right? Which is equal to. Now you will see that the limit is not exist. So it doesn't exist. So we can say f is discontinuous at x equal 4. Or maybe if you want to write but continuous from the left, you could say that, but continuous from the left, because from the left we have the one that we concluded before, the continuous at x equal 1, so we have that is continuous, and then up until 4 it's still continuous, but after that it's discontinuous. You could also say that. But I think if you just write f discontinuous at 4, I think it's enough. But if you want to write the continuous from the left, it's also from the left of the x equal 4. Okay. If you are curious and want to make the graphs, I think it's not that difficult to draw, right? So the first thing is to mention which interval. So 1, and this is 4. So the exponent need to cross 1 here. So we have that one, at least that one, like that. And then should be crossing this 3. Up until this x equal 4, and then after 4, this is start maybe from there, and then that's the square root of x. Maybe not real proportional, but I think it looks like that. It's 2 to the power of x, 3 minus x, and this is square root of x. And you will see that we have jump discontinuity here. So if it is easy to draw, I suggest to draw to confirm the goal. Okay, to end our lecture, please scan this QR code here.